Hello. So I'm going to explain number systems. So first, you know what natural numbers are. These numbers are so basic that you have been using them, I would say, from class 1. 1, 2, 3. These counting numbers are known as natural numbers. And you know why they are called natural numbers? Because I say that these were natural to come to the human mind while counting things, right? And then we have whole numbers. When we include 0 to this collection of natural numbers, we get the collection of whole numbers, right? So it is like when we got 0 to denote nothing, to denote that nullness, nullity, we said humans. Say that now we have the collection of numbers as whole, right? And then we got these negative numbers, these negative integers. So the collection of these numbers is known as integers, right? And so I have also written these symbols, these letters. What do they mean? So this capital N denotes the collection of all these natural numbers, okay? Now we will be thinking of not just individual numbers like 1 is a natural number, 2 is a natural number. No, instead we would be like we are trying to develop this notion of thinking all these numbers in a particular collection, right? So so this n denotes the collection of natural numbers. You know, we cannot get the last natural number. That is like not possible. If anyone says that this number is the last natural number, you can get next one just by adding 1 to this to the current number. Okay. So then we use this capital letter W to denote this collection of whole numbers. And in the same way, we assign another letter, another capital letter, Z, to denote the collection of integers. So these are pretty obvious to understand, but this Z, instead of I, we have used Z. So this is pretty a convention, not something like taken from the name itself, as in the case of natural numbers and in the case of whole numbers, but we use Z, which comes from the German word, as in the textbook it is written, which is Zählen, which means to count. You can also use I to denote the to denote the collection of integers. That is not the matter. That wouldn't change anything, but just stick to the notion, to the notation that we are using in the textbook, so that we all look pretty similar in our answers and in our derivations and in our understanding. So then we have rational numbers. You know that such numbers, you have come across such numbers, right? Like in fractions, and while and in any other way as well. So these numbers, when you include with all these integers, make a new collection, which is the collection of rational numbers, right? So we call these numbers as rational numbers, and this is denoted by the letter Q, which is as previously taken from a word quotient. Okay. Now, now I will give you the definition. I will explain the definition of rational numbers. Then you will see that not only these numbers are rational numbers, but also these numbers are, included in this collection of rational numbers. Okay. In the previous class, you have studied what a rational number is, but let's recall the definition. What a rational number is. So a number R, okay, is called a rational number if it can be in the form P upon Q, where P and Q are integers and Q doesn't equal 0. Okay, so any number R can become a rational number if it fulfills two conditions. What are they? The first condition is that, first of all, it is represented in the form P upon Q, where P and Q are integers and Q is not 0. Okay, so just two conditions. If it fulfills, that number is a rational number, right? So now what we said that the integers are also rational numbers. So how are they rational numbers, right? If we look at this definition and then the integers, let's say an integer 4, right? So how can this 4 be a rational number? Because we know that this 4 can be represented in the form P upon Q as, let's say, 4 upon 1. Yeah, so 4 equals 4 upon 1, right? So 4 upon 1 evaluates to 4. Now, this 4 has been represented in the form P upon Q, where this P and this Q are integers, and in the denominator we do not have 0. And these are the two conditions. If they are fulfilled, the number becomes a rational number. So 4 is a rational number. Okay, so in a similar manner, we can also say that minus 24. It can also be a rational number. Just put 1 or anything to represent it, to write it in the form P upon Q. Let me write it like this: minus 48 upon 2. When you simplify it, you will get this minus 24. Okay, so minus 48 upon 2. This is a rational number. Yeah, yes it is, because it has been represented in the form P upon Q, where P and Q are integers. Minus 42 and 2 are integers, and 2 doesn't equal 0. And that was the condition. Q, the denominator, cannot be 0. We know that. That is so basic to to get that. Why do we insist that Q must not be 0? Because we cannot divide any number by 0. That is the case, and this fact we have observed in our previous classes, so I won't go into that. So since natural numbers are integers, yeah, they are integers. Like, natural numbers are included in this collection of integers, so are the whole numbers. So in a similar manner, now since we have shown that integers are also rational numbers, so we can say that right? So rational numbers include the natural numbers, whole numbers, and integers. So one thing I would suggest you to look at these things, at these names. You can get confused, like why the same number are natural and then they're the same. Like, not all the numbers, but many of them are whole numbers, and then they become integers, and then we have rational numbers. So you would say, what should I say when someone says that if minus 4 is an integer or a natural number? First of all, that type of questions one wouldn't ask. And if someone asks, what would you say? You can say that 4 is a natural number. Yeah, it is. 4 is a whole number. It is. 4 is an integer. It is. And 4 is also a rational number. So, when we say natural number, we have numbers starting from 1 up to infinity. And then when we say whole numbers, we include 0 into the collection of natural numbers. So what are we doing here? We are increasing the extent of the collection, right? Of the collection of numbers. When we say rational numbers, we include many such numbers which were not in the collection of integers, right? But integers automatically get into the collection of rational numbers. Okay, so when we say, so these terminologies help us to define many rules and many formulas, many theorems, which you will see later. So I would say that not need to break your head much about it. Just stick to the definition, and when you will apply these definitions in your questions, in your problems, you will get a good grasp of it. Okay. Now let's move on to the next part. Now, one thing about rational numbers is that a rational number can be represented in many different ways. For example, what do I mean is that if you take 4, not 4, let me take something else. If you write 2 upon 3, right? This is a rational number, right? Now this can also be written as 4 upon 6, right? And also as 8 upon 12, also as 16 upon 24, and so on. Okay? So we can say that a rational number does not have a unique representation in the form P upon Q. The same rational number can be represented in many different ways. As in this case, we have at least three more ways to represent this rational number. So these are equivalent rational numbers. These are equivalent rational numbers. So what I want you to know is that whenever we get any of these rational numbers, so we will be using that form which is in the reduced, reduced form of such equivalent rational numbers. Okay. So for example, if you want to represent this rational number 8 upon 12 on the number line, we will use this 2 upon 3. Okay. And here, as you can see, that 2 and 3 are co-prime. What does it mean? It means that they have no common factors other than 1. So you need to make sure that whenever you represent or write a rational number in the form P upon Q, or you represent that number on the number line, you will always take this reduced form of that rational number. Okay. So that is a very little point to make here. Now let us do some examples, okay? And it will help us to understand what we have been learning till now. So the example says that one of the parts of this example says that every whole number is a natural. So you can also find this example in your textbooks. So you know every whole number is a natural number. So this question is like easy to answer, but what the question wants you to know, or what the question wants you to notice, is that very slight difference, which I have is put emphasis on, and that was 0. This number 0, it is a whole number, but it is not a natural number. Okay. So it says that every whole number is a natural number. So at first, if you are not like that, like if you do not look at mathematics that way, which you are still trying to develop, and that is not bad for you, you have to learn things. So you might say that all the whole numbers, like all the natural numbers, are in the collection of whole numbers. Just only this one number, which is 0, is not in the collection of natural numbers. So why this only number makes the difference? Like when you say that every whole number, so in your mind it might come that 1 is a whole number and it is also a natural number, 5 is a whole number and it is also a natural number. But you have to look at that specific example which counter argues your the statement, right? So 0 is a whole number, but not a natural number. So this statement is false. Another one says that every integer is a rational number. Now this is true. You know that any integer, let's say m, can be represented as m upon 1. So this is true. So I've just written in a very condensed way. You can write in words as well. But what I wanted to say is that your m is an integer, so I must write it like this way. So this makes the statement true. Now the third statement says that every rational number is an integer, which is false. Every rational number is not an integer. You can give any rational number which disproves this statement. So you can say that 4 upon 3, this is a rational number, but it is not. It is a rational number. But not an integer. So this is false. So there's nothing much about it, just basic things to review. So these 3 statements were given. Now the next example says that is important, as I would say. And this is about finding some rational numbers. Let's say 5 here. Sorry, just broke the flow. Find 5 rational numbers between 2 given rational numbers, right? Which are, let's say, between 1 and 2. So there are 2 ways to approach this problem. Let's say first approach as method 1. So the first method is to find a rational number in the middle of it, okay? So let's say if you have 2 rational numbers, r and s, so you take the sum of these 2 rational numbers and then divide it by 2. It is like taking the average of these 2 numbers, and you will get a number which is in between these 2 rational numbers. Okay, so in this way you will get only one number. If you like visualize it using a number line, so if you have, like, let's say 1 here and 2 here, so the average of these two numbers lies in the middle of in the middle of these two numbers, right? So so you have to, like, step by step. You will first get one number in the middle, then you will find another number here, and then one here, and one here, and let's say one here. So in this way you will get 5 rational numbers. So I will do it for you. So yeah, first number can be, so 1 plus 2 divided by 2 is 3 by 2. So 3 by 2 lies here in the middle of 1 and 2. Then we will use 3 by 2 and 1 to find the next number in the middle of 1 and 3 by 2, which is technically in between 1 and 2. So adding 1 and 3 by 2 and then dividing the sum by 2 gives you 5 by 4, right? So 5 by 4 lies here. And then in a similar way, we can use 5 by 4 and 3 by 2 to get another number, another rational number. So 5 by 4 plus 3 by 2 divided by 2 gives you 11.8, right? So 11.8 is here. Let me write it up the line. So we have found 3 rational numbers. Now we need 2 more rationals. You can use any 2 numbers here to find another one. So let me use 3 upon 2 and 2. So 3 upon 2 adding to it 2, dividing the sum by 2 gives you 4 and 3 plus 7. Yeah, 7.4. So 7.4 lies here, right? Then we will use 7 upon 4 and 2. We will find a number in between these two, 7 upon 4 and 2. So it is 15 upon 8. Yeah. So that is here. As you can see that we have calculated 5 rational numbers which are in between 1 and 2. Okay, and you can notice that in this way we can get more natural numbers, like we can get 6, 7, 8, 9, and if you observe this, if you look at it carefully, you can arrive at the conclusion that we can actually have infinitely many rational numbers between any 2 given numbers because of this method, because of this process which we have just saw, right? Now this is method number 1. Moving on to the next method, and that method is more efficient and less time consuming. So method number 2. So what you have to do in this method is that you just you have to write these 2 given rational numbers in the form p upon q with denominator. We have to write 1 as p upon q, and the denominator becomes what? We have to find 5 rational numbers, so we will write the denominator as 5 plus 1. So like number of, how many rationals do you want? That number and adding 1 to it, 1 more. Okay, this is how we make our denominator. And so it is 6, so 6 upon 6, so it becomes 6 upon 6. In a similar way, 2 becomes 12 upon 6, right? If you multiply the denominator by 6, you have to multiply the numerator by 6 so that the number, the value doesn't change. Now, between 6 upon 6 and 12 upon 6, you have 5 rational numbers, and they are 7 upon 6, 8 upon 6, 9 upon 6, 10 upon 6, 11 upon 6. And they are in between 1 and 2. Right? So this method is very efficient and very is good to use than the first one. So now let's do the exercise 1.1. Okay, the first question in exercise 1.1 says that is 0 a rational number? Can you write it in the form P upon Q, where P and Q are integers and Q is not 0? So, as you can see that this question is really like, is trying to check if you have given care to what have been, what have been explained. So, I think many of the students would say that, or would intuitively have this idea that 0 is not a rational number, because they have been looking at the definition and they find that the denominator Q is always checked for not being 0. So but this is not the case. 0 is a rational number because this satisfies the conditions to be a rational number. 0 can be written in the form P upon Q as 0 upon 1. Right? 0 upon 1 evaluates to 0. So 0 has been written in the form P upon Q, where these P and Q are integers and Q, the denominator, is not 0. Right? So it is a rational number. Okay? So you can write, yes it is, or what else? Moving on to the next question, it says that find 6 rational numbers between 3 and 4. Yeah, the same question which we have just did in example, in the second example. So between 3 and 4, how will you find that? So just write 3 as 3 times. It says to find 6 rational numbers, so you will write the denominator as 7. 6 plus 1 more, right? Plus 1. So it becomes 7, 7 upon 7. So 3 becomes 21 upon 7, and in the same way 4 becomes 28 upon 7, right? Now you can easily get the 6 into the 6 rationals. 22 upon 7, 23 upon 7, 24 upon 7, 25 upon 7, 26 upon 7, and 27 upon 7. And these 6 rationals lie between 3 and 4. So these are the required rationals which we were asked to find. Okay? And we have used method number 2 to find these. Now let's move on to the next question, which is, I think, which demands the application of this concept, of this method, more advanced, in a more advanced way. Okay, so it says that we have to find 5 rational numbers between 3 upon 5 and 4 upon 5. So we will use the same logic. What we have to do is that we will change this denominator as this. We will multiply this denominator by 5 plus 1 because we are to find 5 rational numbers, so we will multiply it by 6. So it becomes 18 upon 30, and this becomes 4 upon 5 becomes 24 upon 30, right? Now 3 upon 5 has been represented in this form and 4 upon 5 in this one. So we can easily find the rational numbers. 19 upon 30, 20 upon 30, 21 upon 30, 22 upon 30, 23 upon 30. Now all these rationals lie between 3 upon 5 and 4 upon 5. Okay? So yeah, we just answered the question. So what you have to take from these two questions is that you just manipulate the denominator of the given rationals, and in that way you can get any number of rationals as you want between two given rationals. Now question 4 is of true or false type, and it has 3 parts. So the first part of this question 4 says that every natural number is a whole number. That is true. Yeah, that is true. Because all the natural numbers are in the collection of whole numbers. Right? So this statement is true. And the second part says every integer is a whole number. That is false. Every integer is a whole number. No. -7 is not a whole number. So this statement is false. And the third one says every rational number is a whole number. That is also false. Since we know that 4 upon 3 is a rational number, but not an integer. Okay, so these were 3 statements which we had to tell whether true or not. You can easily tell them